What do you always want more of until you've had enough? Cake, obviously, but also computing resources. Scaling is today's topic, and on today's streaming audio, we're going to talk about scaling Kafka clusters, adding and removing capacity dynamically, and then doing that at scale. Because we're not just resizing one cluster, we're going to resize a whole cloud's worth of them. To take us through it, we've got Ajit Yagaty and Aashish Kohli, who've been taming Kafka and Kubernetes to make the most seamless scaling experience they can. But before we begin, let me tell you that streaming audio is brought to you by developer.confluent.io, which is our educational site for Kafka. It can teach you something new whether you're a complete beginner or an event systems guru. And while you're learning, you can easily get a Kafka cluster started using Confluent Cloud. Sign up with the code podcast100 and we'll give you $100 of extra free credit. And with that, I'm your host, Kris Jenkins. This is Streaming Audio. Let's get into it. My guests today both work on cluster elasticity and capacity management for Confluent Cloud. We have Aashish Kohli, who is a product manager, and Ajit Yagaty, who is an engineer for those teams. Gentlemen, welcome.
Thanks, Kris.
Thank you.
Good to have you here. So we're going to talk about elasticity and specifically cluster elasticity, but maybe we should start with the word elasticity. Maybe I can give you my lay definition of it and you can tell me what I'm missing. I think of elasticity as two constraints, right? I never want to pay for more than I need, and I always want to be able to buy as much as I want. Aashish, do you think that's about the size of it?
Sure, I think you got that right, Kris. When we think of elasticity, it's literally it's a table stakes for a cloud service. Any cloud service today has to have the elasticity capability sort of fully satisfied. And the idea here is that just think of any utility that you use. You pay for a utility in terms of how much you use. You don't have extra capacity lying around all the time. Same way for a cloud service with elasticity, the idea is that you can very closely align how much you're using with how much you need, and so that you never have excess wasted capacity, while at the same time, you don't have situations where you need that excess capacity and you don't have it available. So it's the close alignment of your demand to how much is being available to you as a consumer.
Yeah, should be like turning on a tap right in the kitchen. You want some, you get some. You turn it off. You always get as much as you want and no more, ideally.
Exactly.
So, okay. Do you know? I've just thought of another thing which I think is important. There should be minimal manual user intervention, right?
That is true. That sort of goes into the domain of auto scaling. Elasticity is basically the capability of being able to add or remove capacity. But manual intervention also goes into the aspects of auto scaling, which I think we can talk about that in the discussion as well. But yes, you're right.
Yeah. Okay. So let's translate this into our favorite world of Kafka, right? So, what? Give me an overview. Before we get into the cloud, what do I need to do when I'm hitting capacity problems? Where do I start?
Start with Kafka, you mean?
Yeah, so like my Kafka cluster is somehow reaching its limits. What sort of limits am I going to see, and what would I, if I were managing it myself, do next?
Sure. So when you think of Kafka clusters in Confluent Cloud, we have this abstraction called CKU, or Confluent Unit for Kafka. The way a CKU works is it gives you some capacity along 7 different dimensions. And the reason we have this notion of a CKU is because we've abstracted sort of the underlying infrastructure details that you might worry about if you're self-managing Kafka, open source, or even running it on-prem. And the idea is that when we give you this abstraction, you can expect the same kind of capacity or performance as you migrate across clouds. So if you were self-managing Kafka on AWS versus GCP, you would have to go and try and pick different kinds of instances, whether they are memory optimized or compute optimized. And you would have to understand what performance you can get from those instances and what you should expect from your Kafka cluster. We have sort of abstracted all of that away. So you as a customer don't have to worry about all of these differences between clouds. And we give you a CKU as a unit of capacity, and you can get X number of CKUs on your cluster. And that guarantees the same kind of performance across different clouds. So you don't have to worry about all of those underlying details, and you can just focus on getting the right capacity from your cluster.
Okay, I see what you're saying. So does that actually works in practice, that I can stop worrying so much about the balance of disk and capacity and CPU? It's got a fairly
Absolutely.
predictable workload in that way.
Yeah, absolutely. I mean, that's the whole promise of us as a fully managed SaaS service, that we don't want you to worry about those underlying infrastructural details. We also have benchmarks that we publish, saying this is a 2 CKU cluster and this is the kind of performance you can expect. But we also recommend customers run their own benchmarks, because the performance you can get from a cluster also kind of depends on your workload, how many clients you have, how many partitions you're creating, and how you're distributing that load. So we always recommend that you go with our benchmarks, but you should also run your own workloads and see what kind of performance you get.
Okay. So then I was thinking in terms of CPU or disk, but you're saying I can start thinking about hitting some limits in this abstract unit, right? But what's the shape of a limit? I find that things are slowing down. I find that it's taking my is it as simple as my throughput drops and I think, oh, I need some more capacity?
Sure. So the 7 dimensions of a CKU, and let me see if I can remember them. I probably won't be able to rattle off all of them, but it's basically storage, which is getting mostly unlimited across all three clouds because we've moved to tiered storage. But
Hmm.
it's ingress and egress, so throughput, and then number of partitions in the cluster, connection attempts per second, request rate, and I forget there's a seventh one. But the idea is that each of these dimensions, we specify that if you have a 1 CKU cluster, you can get 4,500 partitions, or you can get an ingress of 50 megabytes per second. As you up the number of CKUs, you get more and more from each dimension, just multiplying it by how many CKUs you have. So as you're running a workload, it depends on how much you're consuming along each dimension. In general, you are not able to max out all of the dimensions at the same time. So how much of you are getting in your cluster from one dimension kind of depends on your overall workload.
Right.
And what we've sort of done to make that easier for customers to understand is we've recently launched what's called a Kafka cluster load metric, and that tells you what the overall load on your cluster is. It's a holistic metric that tells you the performance of your Kafka cluster.
Where do I see that?
You can see that in the UI. It's also available from our metrics API. So if
Okay.
you go to the Kafka Confluent Cloud UI, there's a capacity settings page for the Kafka cluster that has a gauge that tells you how much load you have on your cluster. It's a value between 0 and 100, as well as it's available through our metrics API. And that's how we really think most customers might end up using the load metric, is by
Mm.
querying the metrics API and getting the value.
Okay. So there are a few of these different metrics I would then need to worry about maybe stepping up my capacity.
Yeah, I think
So,
in general, when you're thinking of stepping up or stepping down capacity, it's the load metric you want to worry about. The other metrics, the 7 dimensions of a CKU, is basically your usage, and you might get throttled along some of those dimensions if your load is approaching a high value of, say, 80 to 90%.
okay. So I know you've been working on the elasticity of this, but tell me what the world was like before you started work. What would I do when I ran out of capacity?
Yeah, so I think, I mean, I can probably step back and tell you about the journey we've taken in Confluent Cloud for our customers. So I think years ago, when we first launched Confluent Cloud, we didn't even have the ability for customers to self-serve and provision their clusters. Like, we just launched the service, right? So we would provision clusters for them. The first step we took
Right.
along that dimension was really giving customers the ability to self-serve and provision their clusters, both through the UI, API, and CLI. And then the next step for us was cluster elasticity, so expanding and shrinking clusters. Prior to this, prior to launching the load metric or full elasticity, you would probably have to look at the CKU dimensions and see what the usage is. And if you were running out of usage along some of those dimensions, you would probably contact our support team, and we would potentially do something to add capacity. But today, you have the ability to do that yourself as a customer, right? You can go to the UI or call our APIs and add or remove capacity depending on your usage.
Right. So it would have been a support call before this work.
Yes.
Right. Okay. That's bad for everybody.
Yeah.
As
We
much as it's
are.
nice to talk to engineers.
Yeah, we our goal as a fully managed SaaS service is that we want you to be able to sort of control the aspects of your cluster and take over the burden as much as possible of running the service so that you can focus on your business. So we never want you to have to be able to reach out to support unless it's like a dire situation, like the service is down or something. But other than that, we want customers to be able to fully self-serve, and in most cases also not even have to worry about having to increase or remove capacity.
Right. Yeah. So, Ajit, let me grab you for some technical details.
Sure.
You being the software engineer. So,
Yeah.
let's start with what you would have done behind the scenes if you got that support call to change it, and then you can start telling me how you automated this. Right.
Sure.
What does it take to expand a cluster with Kafka?
Yeah, so I think before we get into that, one thing that we have to clear out is that Confluent Cloud is a Kubernetes shop. I mean, almost all of our infrastructure runs on Kubernetes,
Okay.
and including the customer's Kafka cluster or KSQL cluster. So all of those things also run on Kubernetes. So prior to actually having this specific feature, right? Like if a customer would see that their load is increasing and they look at those specific metrics and they decide that they have to expand the cluster, right? So they would open up a support ticket, and that support ticket would come to the engineers and typically the on-call folks who would be receiving that ticket, and it was a manual process that we had. Like you had to update state in a database and then generate certain configurations and then go ahead and actually bring up the compute, storage, and networking on the Kubernetes cluster. Like so in the Kubernetes world, right, like all of our we kind of make use of a pattern called as operator pattern within Kubernetes. It allows us to kind of extend the Kubernetes API. So we have a service that that does that. So all of our Kafka clusters, customer created Kafka cluster or a KSQL cluster, right? They're all kind of defined by an entity called as custom resource definition. Right? This is again a Kubernetes concept. So where you can define what your resource looks like. For us, a resource would be like a Kafka cluster or a KSQL cluster. And let's say if you're talking about Kafka itself, you would specify the number of brokers that needs to be part of the cluster, how much storage each broker should have, what is our networking story there, and the configuration of Kafka cluster itself, right? So all of those things are kind of encapsulated in this custom resource, which we would generate, and then this operator service that I spoke about would go ahead and expand the Kafka cluster for the customer. And the customer's cluster would get expanded. We would monitor it once it's all done. And by the way, there's also a data balancing part of it. Like you're adding new resources to it, so you need to balance the data out. Or the load out across all the new brokers that have come. So we need to do that, and once that is all done, we would actually let the customer know that we would close the support ticket saying that, hey, your cluster has been expanded, and the customers would get to know. So as you can see, this was like a multi-day ordeal. Multiple teams had to come together to make this all happen, which was a considerable toil. So that's how we used to do earlier.
Okay, crikey. So we should split that up into pieces. So,
Yep.
Because I definitely want to talk about the kind of logical rebalancing once you've got the resources separately.
Sure.
I want to dig into that. So, but I know precious little about Kubernetes beyond the marketing. So take me through how you change that into an automatic process.
Yeah, sure. I mean, Kubernetes is a container orchestration platform that's almost a standard cloud native standard these days, right? And it has a simple yet powerful pattern called as the controller pattern, where
Right.
you have a specific resource, you define the desired state of that resource declaratively, typically a YAML file, and you present it to Kubernetes, saying that this is how my resource should look like. And once that is an input to Kubernetes, and there will be a controller that would be running specifically for that resource, and that controller would get that input, and what it actually does is it compares the actual state of that resource with the desired state, and if the actual state has deviated from it, it would try to bring the actual state towards the desired state. So it's like a continuous on-running process. Like if the actual world deviates from the desired world, it'll bring it back to the
Okay.
desired state. So it's kind of a declarative API that is there, and yeah, so that's the nicety about the Kubernetes, right? And for us specifically, one of the value adds from Kubernetes is that it kind of serves as a cloud provider abstraction layer. So we are available on AWS, Azure, and GCP, and we don't ever have to call the cloud provider APIs ourselves, right? Like to get the resources. So we use Kubernetes. Kubernetes actually kind of abstracts that all out. Like depending upon where the Kubernetes is running, like which cloud provider it is running, we have a standard Kubernetes API that we would say, hey, get me some compute, and Kubernetes underneath would talk the right cloud provider API to get the resources for us. So that's one of the value adds that we get out of Kubernetes. Yeah, I mean it has its rough edges, Kubernetes in general, but I think the benefits that we get out of it far outweigh the pain that we have to deal with the idiosyncrasies. So yeah, I mean that's our standard. Like that's the infrastructure layer that we have, and we kind of put it to good use. We extend the Kubernetes API, like I was specifying, to manage our resources.
So so presumably in the old days you were just changing the controller definition on a per customer basis, and that got you to the first base.
Exactly. Yeah. So everything. Yeah. The way things are laid out, right? Like. Maybe we can talk about the overall cloud architecture that we have, and maybe then that would actually tie the story together. So like I said, everything runs on Kubernetes, and our Confluent Cloud architecture itself is like it's like a decoupled architecture that we have with two main components. One of them is a centralized control plane. It's a global control plane with its own database where it would store state, and a control plane is responsible for orchestrating the provisioning requests, deprovisioning requests. With the advent of the capacity elasticity features that we added, they're also kind of orchestrated by the control plane, right? And so let's say as a user you are interacting with the Confluent Cloud UI or the CLI or API, all of those requests kind of funnel into the control plane. That's where the journey starts, and then we have something called as a data plane. The control plane is referred to as mothership in our parlance, and then we have this data plane, which are again Kubernetes clusters, and that's where the customers clusters would be running, like customers Kafka, KSQL, or Connect cluster would be running in the data plane. And now these two disjoint entities are tied together by a Kafka bus. So we kind of use our dog food, our own technology there. So the Kafka bus is responsible for ferrying the instructions from the control plane to the data plane, and it also shunts the status updates back to the mothership from the
Okay.
satellites. So that's a very high level overview of the Confluent Cloud architecture itself, and within the data plane, right, that is where the component operator service runs, and that is the component that kind of extends the Kubernetes API. Like we have a CRD definition, which kind of encapsulates how a Kafka cluster should look like, right? Like I was explaining about that, like details about compute storage, networking, all of that is encapsulated in that. So now, for every single customer cluster that we have, there'll be one instance of that definition. that is that the CRD is like, we can think about it as a class in OOPS paradigm, and
Right.
the custom resource is like an instance of that class. So we have one instance for every single Kubernetes, every single customer cluster that we maintain.
Is there one class, if I can use the same terms, is there one class for all customers, or are there slightly different ones for different needs?
Yeah, so the content of that, I mean, the class, actually, the fields in the class are common across all types of resources that we support, but then you would instantiate them one for every single customer's cluster. So like if as a customer, if I have 10 clusters, there would be 10 instances of that CRD running in our infrastructure. So,
But do you have
it's,
like we've got an enterprise class that gets
oh
instantiated
yeah,
for all the
sure.
enterprise customers, or?
Exactly. So yeah. So basically, it depends upon. Yeah. So like you said, if it's an enterprise class. We have certain offerings, different types of offerings that we have. Like if as a customer, if I'm using the UI, I could create like a standard Kafka cluster, which is essentially our multi-tenant offering. You would get a sliver of that big cluster that we would run, and you would interact with that. The other option is that you could create a dedicated cluster too, like where the entire cluster is just designated for a given customer. So in these two things, right, like where the multi-tenant offering that we have, there'll be one instance of that CRD representing that multi-tenant cluster that we run internally, and for every dedicated cluster that gets created, there will be a separate instance managing just that Kafka cluster.
Okay.
Yeah,
Right.
and the configurations that we add within the thing it differs depending upon what type of cluster you are. Like a Kafka cluster's configuration will be completely different from a KSQL cluster's configuration.
Yeah.
But the class that we have kind of encapsulates all of these things, and the data that we store within the objects themselves differ based on the cluster type. So.
That seems like a lot to figure out both technically and from a product perspective, right, Ashish? Deciding what shapes you want to offer to people.
Yeah, and I think the idea there is that we want to give people the right kind of capability. I mean, if customers need dedicated clusters for certain reasons, whether it's be compliance or regulatory, we want to make sure that they have that available. While at the same time, our multi-tenant clusters are fairly powerful to handle a lot of workloads.
So the scalability part, you're changing that instance. You're flicking a switch that changes which instance you've got of that class, right?
Yeah,
and then
that is correct.
Kubernetes just magically fills in the rest of the details. Is that right?
Yeah, I mean, there is some amount of shepherding that we have to do in the sense that yes, the custom resource definition that is there. So we need to change it to say that. So let's say you were running a 2 CKU cluster that kind of maps to our internal representation in terms of number of brokers. And let's say you go to from 2 CKU to go to 3 CKU, then that translates to the additional brokers that are needed, like additional storage, networking capability, and the compute that is needed, right? So all of those things kind of get encapsulated. The CRD gets modified. So maybe we should just walk through the whole flow. That way it's kind of clear. So as a user, I jump onto Confluent Cloud UI. Let's say I just choose the UI to be my initiating a point, and in the UI I say, hey, expand my Kafka cluster from 2 CKU to 3 CKU, and I hit a button, expand, and that request comes to the control plane. So the control plane level, what we do is that so for every, like Ashish was explaining the dimensions of metrics that we maintain, right? So those are actually quotas for us internally. Like we have certain things like for every CKU we can actually have 4,500 partitions supported, and there's a ingress and egress bandwidth that we can a throughput that we can support for a given cluster, right? So those quotas will, if it is an expansion, then we have to update those quotas, saying that because the customer is asking for more resources, so naturally the quotas will also get updated, and then the configuration also gets updated because we are saying that we are now saying that you'll be adding more brokers into the cluster, so that configuration details will get updated, and and then the control plane would store this information in its database. Right, and then we kind of have this event-driven, what do I say, event-driven approach, where once the state is stored in the mothership DB, we based off that state, based on change data capture, we generate the CRD instance that I mentioned about, the custom resource definition with the new details in it, and that gets pushed down to the data plane, which is the satellite, through the Kafka bus. And that CRD arrives at in the Kubernetes cluster itself. So once that is there, the operator service that is running, which essentially runs the controller for this resource, right? So that gets notified saying that there's a change that has happened. So then the operator would get in and figure out what exactly has changed. So in this case, we are expanding, so we need to bring up more compute. We have to allocate more storage and also set up the networking part of it. So the operator goes ahead and does that. Like it brings up the in the Kubernetes world, compute is represented by a pod. That's where the Kafka broker would run. It's a containerized. So a pod can actually run multiple containers. So one of the containers would be our Kafka broker itself. So it will go ahead and bring up those new brokers. Then it will also, as part of this bring up, it will also attach the storage that is necessary, right? And then and the networking part of it is taken care of. Now at this juncture, right? So now that the resources have been brought up, but Kafka, we need this additional step of balancing the data. So that's where
So let me just check I've got the first bit, and then I
Sure.
want to move on to the logical rebalancing. So you're saying that the control plane is writing a YAML file and sticking it in a topic, and eventually the data plane is going to pick up its new YAML file and just do as it's told.
Exactly. I mean, that's at a very high level. That's exactly what happens.
Okay, that's cool.
Yeah.
Okay, so now you're in the position where you've got a cluster that has a lot more capacity, but there's a logical step, right? You've now got to make use of that capacity.
Exactly. So
take me through that.
Yeah, sure. So one of the features, this is where we kind of make use of a feature in Kafka called the self-balancing cluster feature. We kind of put that to good use here. So one of the capabilities that like the name suggests, it's a self-balancing feature that it has. So one of the cool things about that is that when you actually add new brokers into the cluster, so it has a way to figure that out. Like, typically in the Zookeeper world, these new brokers would register with Zookeeper, and then the SBC component running inside the brokers themselves would know that there are new brokers arrived into the cluster, and then what it does is that it kind of adds them into the cluster. So it's called an add broker step. So what it essentially does is it figures out what is the current utilization of the cluster, and there's new resources that have been added to it. So it generates a plan to figure out how should the rebalancing look like, and then it starts moving the data over to the new brokers that have been initialized. This kind of happens automatically. So the moment we bring up the new resources from the operators from the data plane service, right? The moment it brings it up, Kubernetes brings up the resources. SBC kicks in. It starts the process of rebalancing the data. While this is happening, from a customer's point of view, the cluster is still not completely rebalanced. So we wouldn't tell the customer that your cluster is already expanded. So as a customer, right, in the UI, I would see expanding as my status. So now the operator would have to poll like this the amount of data. So the rebalancing means that we are actually moving data around, right? So while that is happening, the operator actually has to wait for the rebalancing to complete. And once the rebalance is completed, that's when we kind of send the status information back to the control plane via the Kafka bus that I mentioned, saying that the rebalancing is all done now. And then at that point in time, there'll be a notification sent out to the customer saying that your cluster has actually expanded, and then the UI would also show the status accordingly. So one of the key things to remember here is that we do have like Aashish was saying, the customer would be charged for the resources that they use, right? So in terms of expansion, we would start charging them only after we have rebalanced the cluster completely. Even though we have brought up the resources up front, we don't charge for that. We charge them towards the end. For shrink, it's the other way around. Like we kind of charge them up, reduce their bill up front, and do that. So this is the life cycle. Like once the operator figures out that everything is rebalanced, it would send a notification back to the control plane, and the control plane would then notify the user saying that the expansion is completed.
Okay. Out of interest, how does it happen the other way around? What's the flow of commands and control?
Yeah, so predominantly the flow remains the same. I think the magic is where the operator part, the operator component, right? The interaction with Kafka is where the heavy lifting is. So the again, as a shrink, customer clicks a button saying the shrink my cluster, and it we update the quotas again because we are reducing the size. So naturally we have to update the quotas for the CKU for the CKUs that have been chosen, and then we send out a notification to our billing service saying that start charging this customer lesser because they've shown their intent to reduce the cluster size. So it's kind of favorable to the customer that way. And then the request flows down to the data plane. So here in this world, right, like in the shrink path, first we have to move the data out of the existing brokers. We can't bring them down, so we need to, because that would lead to availability issues, right? Like so we wait for the data to move to be moved out. Again, we use the self-balancing Kafka self-balancing cluster feature here. So for this we kind of developed both the SBC team and our team work together to come up with APIs that makes this integration much more smoother. One of the things that one of the guarantees that is there is that any of these things can go down at any point in time. It's a distributed system. And the interactions that we have between the operator and the SBC, right? So there are some guarantees that we would need. So one of the things that we have ensured with these APIs are that they're idempotent in nature, because you call a request, you call an API, and the operator can go down and come back up for whatever reason, right? And the operator kind of picks up. It just stores enough state so that it can restart the state machine of any of these operations that are being performed, right? So those APIs, if they are idempotent in nature, it is helpful. So that is one thing that we kind of built into the system. And the other thing is that we remove multiple brokers at a time. Because a single CKU can actually map to n number of brokers, and it would make sense to actually remove multiple brokers at the same time, because let's say for examples, like one CKU maps to, let's say, 10 brokers. I mean, just an example, right? So if you move, if the user's intent is to move all the 10 brokers. Now, if you move one by one, there's a lot of wasted effort that is going on, right? We keep moving the data. Yeah, exactly. Yeah. So it takes a long period of time, and also we are moving the same data over and over. So that's why we try to do remove multiple brokers at the same time. And this API that we SBC folks did a wonderful job there. So one of the design aspirations there was that this API to remove multiple brokers at the same time would be atomic. Like if anything fails in between, none of them will be removed. But if it succeeds, all the brokers will be removed successfully out of the thing. So I'm sorry.
That's going to be hard to implement.
Yeah, that's why I said, like, I think the heavy lifting was done on the SBC side, so the operator's life became easier because of that. There's very little things to reason about. If an API fails, we know exactly what has happened, and we can just continue from where we left off. In the shrink path, again, we call the remove broker API from the SBC world to remove the brokers. I mean, to move the data over first. Once all the data has been moved over, we bring down the brokers in that particular cluster. So one thing to keep in mind is that while this is all happening, right, we don't want newer data to go on to the brokers that are being removed. So SBC again provides this exclusion part. So the moment we say, hey, remove these brokers from the cluster, Kafka SBC would ensure that no new topic creation or no new configuration changes would place newer data onto the brokers that are being removed. That way, there's only a finite amount of movement that we have to do. Otherwise, you can be in this phase where you're trying to move, but there's new data arriving, and you will never converge. So that is another feature that is quite important here. Yeah. So yeah, the overall flow is just that. You remove that, and you wait for the removal to complete, and once that is all done, you would bring down the storage, the compute, and networking for those brokers, and then mark the operation as successful and send it back.
So on the way down, it's actually structurally very similar, except the controller needs to know to rebalance first and then take the resources away. And most of that it actually delegates to the SBC.
Yeah, so the heavy lifting, like the actual data movement, is done by SBC. The operator just shepherds the whole process. It just calls the API, waits for the API to say it's all done, and then it goes ahead and update, removes the Kubernetes resources that are not needed anymore. So in all of this, right, like if you think about it, the movement, the data balancing part is quite heavy in the sense that if you have, it is a function of how much data you have. So one of the nice things about Confluent Cloud, at least on, we have the tiered storage feature, right? Like only a hot set will be stored. That means that the amount of data that is stored locally on a storage attached to every single broker, right, is very small.
Define very small.
Yeah, so it's this is a Kafka. The typical use case is like an event streaming kind of a thing, right? And more in such use cases, there's a producer and a consumer, and the consumers are mostly interested in the latest data that has come, that has arrived. So we kind of define that as the hot set. So let's say last 30 minutes of data is what we are interested in. I mean, right? Like so only the last 30 minutes of data will be stored locally, and beyond that, everything gets tiered to like an object store in the back end, right? So the amount of data stored for every single broker locally will be small, and this aids in the data movement too. Like we can be done very quickly. Like removal or addition of new brokers will be very quick because there's very little data to move around. So that is another feature that kind of makes the elasticity story quite good. Like otherwise there's huge amounts of data we have to move. So the amount of time it takes to handle these requests will also be larger otherwise. So yeah.
Cool. Okay. So that kind of relates to back to the producty end of it, Aashish. How long does this process take? What's the user experience of this?
Sure. So I think per CKU, it can take a couple of hours to expand or shrink the cluster, and it varies. I think, as Ajit mentioned, the two. If you step back and think of this whole expansion or shrink process, is like two main steps. One is addition or removal of brokers, and the second step is this data rebalancing before we tell the customer your cluster is ready with the expanded or removed capacity. The cluster is available through this whole process. But the second step is very critical, and the time it takes for a cluster to expand or shrink really depends on the size of the cluster. So how many CKUs you're adding or removing, because that's wherein comes the number of brokers you need to add or remove. So that's one step that takes time. And the second step is how much data there is on the cluster. So as Ajit mentioned, the concept of tier storage, like sort of decoupling compute and storage, that allows us to have much less data on the brokers that needs to be rebalanced. So it's definitely made things much faster. But even so, depending on one cluster versus another, the amount of data on the brokers that needs to be rebalanced will affect how long it'll take for the overall expansion or shrink process to complete.
But it's a matter of hours rather than the days.
Yeah, it's definitely not days. And I mean, we're always optimizing things to make it faster and faster. But I mean, if you think about it, in these two steps, we could, let's say you're expanding a cluster. As a service, we could really say, hey, you're going from 2 CKUs to 4 CKUs. We've added these brokers, and here's your cluster. It's expanded. And that would be super fast, like much faster than having to rebalance the cluster and saying expansion is done. But in that case, we are doing our customers a disservice, right? The idea is that we are a fully managed SaaS service. We want you to focus on your business. It's our job to give you a cluster that performs well. So that's why we add the brokers, we rebalance the data. We don't want to give you a cluster where you need to go ahead and rebalance the data to optimize it for performance. So that's why it takes a little bit longer, but it's the right customer experience where we take care of both of these steps rather than having the customer worry about any of the operational aspects.
Yeah, that makes sense. So speaking of customers, right? Like, you probably can't tell me specific customers, but tell me generally how customers are using this out in the real world.
Yeah, so I think you can think pretty much all customers that are using a cloud service that have any sort of variable workload
Mm-hmm.
will want to use cluster expansion or shrink. The scenarios could fall in certain categories. I mean, I think Black Friday comes to mind as the most obvious use case where retail customers might want to add more capacity going into Black Friday.
Yeah.
And then after the season is done, so there's a seasonality aspect to it. And after the season's done, they might want to shrink it down to sort of what their average workload is. At the same time, there are other aspects where maybe airlines going into the summer might want to do something like this because in
For a
the
very
summer,
wide season.
yeah, travel
Yeah.
season and stuff.
Yeah.
Gaming companies might want to do it right before a game launch because when a game launches, there's all this interest, and then over time they can sort of reduce their capacity.
Yeah.
I think going back to the sort of the timing aspects of this, how long it takes. I think when we talk to our customers, we tell them not to think of this as a daily or hourly experience where you're just adding and removing capacity all the time. You kind of have to plan a little bit because adding capacity, rebalancing the data does take at least a couple of hours, and the more capacity you're adding, the longer it'll take. So I think we want them to think about this more in terms of days or weeks rather than just like every hour you are increasing or removing capacity.
Right. Yeah. Okay. So where is that going to take us into a future where things are a little bit more fine-tuned?
I think again, I think I touched on this earlier in the conversation. When we think of our customers' journey, we've given them the ability to self-serve their clusters. We've also now given them the ability to expand and shrink their clusters, and that experience is same from the UI, APIs, or CLI, whatever you might want to choose. Most customers we think will likely use the APIs to sort of include this expansion and shrink into their overall workflow. But and we can stop here, right? We have given customers the ability to create clusters. We've given them the APIs. They can program these APIs. They can watch the load metric, and they can expand and shrink their clusters. So technically, we can say we are done, and we've given customers all of these primitives. But again, thinking of the customer's experience, now a customer that wants to do auto scaling, that doesn't want to have to worry about tracking the cluster load and expanding and shrinking, would have to instrument something where they sort of stitch together these APIs and say, hey, by the way, when my cluster load goes above 80% and stays there for 24 hours or 72 hours, add 2 CKUs to expand the cluster. That would be then on them. But that would be a disservice to them. So we don't want to stop here. Our next step, which we are thinking about, is what we refer to as policy-based scaling or auto scaling.
Right.
And the idea there is that customers can define some sort of minimum or maximum CKUs for their cluster. And we can, based on the load, basically say anytime the load drops below 30% and stays there for some time, we shrink the cluster down by a CKU or 2 CKUs. If the cluster load has been over 70% and sustained for some time, we start expanding the cluster. So that's auto scaling that customers can set their policies, and we'll do it for them.
Cool. What's your timeline for that, or are you not giving deadlines?
Yeah, I mean, as a product person, I am very careful about giving timelines, but that's something we are
Very
actively
wise.
thinking about. I think our goal is to, as I said, take over all of the burden of running the service or tuning the service from our customers. So it's definitely something we are very strongly thinking about, but I cannot go into timelines, unfortunately.
Don't make commitments. Yeah, that's fair. That's fair. It does make me want to just check one technical thing, and either of you can field this, is if you're in this world where it was automatically shrinking and growing, or today when you're manually doing it, does the process of shrinking or growing affect performance? In that, if I say grow my cluster, will it slow down a bit before it speeds up?
Well, I can say something, and then maybe Ajit can chime in. I think one thing I want to cover about expansion and shrink, I think, which we didn't get into, is that I think Ajit touched on the billing aspects, that when we expand a cluster, we start billing at the higher CKUs at the end of the process. When we shrink, we start billing at the lower CKUs at the beginning of the process. So it's very customer friendly. At the same time, when we think of cluster expansion, we can be a little bit more aggressive about it because we are adding capacity, right? We are, from a cluster's performance perspective, we are adding capacity, so we can add more capacity faster. When we are shrinking a cluster, we try to be a little bit more conservative because, again, we don't want to affect the load on a cluster while we are doing these operations. So when we are shrinking a cluster, we'll warn you in terms of the cluster load being high or certain limits that you might be hitting, and there are safeguards in place to prevent changes that will affect the performance of the cluster. Other than that, while the process is happening, the cluster is available and running. So there should not be any noticeable impact to the cluster's performance in terms of the capacity that's available. I don't know, Ajit, if you want to chime
Yeah,
in.
I mean, like let's say if you're expanding, right? Like when the cluster has from the UI, let's say you initiated an expansion and the UI says that now the cluster is expanded. That's when you kind of we expect the customers to start pushing in more data. But while this is happening, right? So like we are rebalancing stuff. So in Kafka, every the way people store data is that there is a topic, and then every single topic is actually has n number of partitions, and these partitions are evenly balanced across the number of brokers that you have. So as part of the rebalance, right, like we would be moving some partitions over to the new brokers. Once the movement actually happens, right, so from a client's perspective, when they're trying to access that, we have the smart clients that figure out, oh, the partition does not reside on broker number X, we have to go to broker number Y. So it figures that out and then and goes to the right broker. But then that also means that for that particular partition, you can if there was any performance deficiencies that you were seeing, you can start pushing more data into the cluster at that point in, like, so it depends upon where we are in our rebalancing phase. So that's why we say that once the cluster has says that it is already expanded, that's when you would be able to realize the full potential of the cluster.
But there is going to be a slight rebalancing phase, just like you would with if you added more consumers.
So whatever performance they were getting before, they would continue to get it. Only that the guarantee of getting more performance out of the cluster is served only after the cluster only after we say the cluster is completely expanded.
Okay. Yeah, that makes
with the rebalance complete. Yeah.
Okay. Cool. Well, I mean, it's obvious why it's an important feature, and I can see it's usefully done. And I think I've got a good sense of how I could be dangerous enough to try and implement it myself in the mythical business that exists inside my head. So thank you very much. That was very enlightening. Ajit, Aashish, thank you very much for joining us on Streaming Audio, and I hope you'll join us another time.
Thank you, Chris.
Thanks a lot. Thanks for having us. Cheers.
And that brings us to the end of another episode of Streaming Audio. The episode with so much scale, we needed to double the number of guests. If that leaves you wanting to kick the tires of cluster scaling, you can give it a try at confluent.cloud. Sign up with the code podcast100 and we'll give you $100 of extra free credit. And if you're still learning how this world all fits together, well, take a look at Confluent Developer, which will teach you everything you need to know about Kafka and event streaming. And if it doesn't, let us know and we'll add it. For that, or anything else you want to let us know, head to the show notes for our contact details and my Twitter handle. Or if you're watching this on YouTube, leave a comment or click one of the friendly thumb icons they have. We'd love to hear from you. And with that, it remains for me to thank Aashish Kohli and Ajit Yagaty for joining us, and you for listening. I've been your host, Kris Jenkins, and I'll catch you next time.